Chat, did you see how I dropped that secant line?
Wait, Drew.
Can you say that?
Chat, what's the average rate of change, chat?
Ew, I hate when people say chat.
You guys are not chat. You're chefs. Hello, chefs. Welcome back to section 2.1. Okay.
But is only our class chefs, or is everyone chefs?
Like
whole grade?
AP Calc
Or all
right
chefs?
now are all the chefs.
I like it.
Can
What
we be
about other
like?
classes?
Can we be?
Last year's group, remember, was Hey Chat.
Chat.
They were chat. And the year before that was AP
Chat.
Calpers.
Wait, can we be something a bit like deeper than? Can we be like head chef, like line chef or something?
No,
Mr. Cheswick had the idea
Chef is not
that you
breaking
guys,
up.
following Brat Summer, that you guys be brats. And I say, hey brats.
We
So
can do
on
it.
my email, I was like, I don't know enough
Alright,
about
what
this.
I feel like the thing
Yeah.
about summer's trends is that they kind of fall
Well,
off.
and
as a
Leo
fall.
made me an AP Calc AB, like the green and the black, to use for a thing. But anyways, we're going with chefs.
What about
Unless
Skippy
somebody else
slicers?
can find.
Skippy.
What?
Skippy slicers.
Skippy slicers is so much
Yes.
better.
Give me toilet
No, not
biz.
Duda. Not toilet riz.
Okay.
Skippy slicers.
Okay.
What is Skippy slicers?
Should we just like start over? Let's just start over.
No,
started.
no, you
Wait,
can't go from
who are we
chat to
missing? I
chat.
feel like we're missing a ton of people.
It's
Jay,
a mess,
It's Jay.
Where's Jay?
Sick. This is why we're recording right now.
Can
Miss you, Jay! Can you hear me?
I text him and say wish you well?
She's stopping recording.
Okay, I'm recording.
He was
No, I
texting me
didn't.
so late last night. How is he?
Okay.
She was texting like at.
That's why you say
I don't want to know. All right. So last time in section 2.1, we introduced the idea of calculating or thinking about calculating rate over an interval versus rate at a particular point. And the example that I had given you guys of to introduce, we were looking at some data on COVID-19, where we were thinking about the independent variable being time in days, and then the dependent variable was number of new COVID-19 cases per day. And you guys calculated the average rate of change, right? The average rate of increase of number of new COVID-19 cases over an interval of time. I think it was like March 1st, 2020 to March 11th, 2020. And you guys discovered to do that, you used slope formula. And I told you guys that that was actually calculating the slope of the secant line, right? Slope of a secant line. A secant line is a line that intersects a curve in 2 points, okay, where the points are the endpoints of the interval. And this brought up average rate of change versus instantaneous rate of change. So rate of change over an interval of time versus rate of change on a particular day. So we started talking about, in general, how to calculate average rate of change of a function over an interval, right? So if we have an interval of x values, so x sub 1 to y, or sorry, x sub 1 to x sub 2, and you're calculating average rate of change over that interval, we have x sub 1, x sub 2, the points on the graph, and then you draw the line that intersects those 2 points, or passes through those 2 points. That is the secant line, and it is the slope of the secant line that gives you the average rate of change of the function values with respect to x. So meaning, on average, as x increases, how are the function values, how are the y values increasing on that particular interval? Are we okay with this? So this is where we ended off. I'm going to think about taking, and I also had us think about relabeling our slope formula for slope of the secant line using function notation. I want to take that same picture now, but I want to relabel it. So I'm just going to copy and paste down here. Let me make it a little bigger. Okay, so this is still the secant line. Oops, where's my eraser? Why does it keep switching?
Does that? Oh yeah, it's because like it's a new feature. Yeah, whenever you erase
so like
It's so...
You can turn it off in settings.
Oh.
but sometimes it's actually useful.
I like it.
But then, like, if you do.
Why does it keep switching to this? What do I do?
If you go to settings, if you go to handwriting, if you deselect auto deselect eraser, then it.
If I do this,
Should I do it or not? I want to keep
and I erase Y, it goes back.
Oh,
to
thank
the
you.
Yeah, that's how you do it.
And so it's like if I want to erase, okay,
Two
I'll erase
things.
this.
Oh, right away, right
If
away.
I wanna erase
Last
this
time,
and then this.
before, you would double tap it and do that.
Okay, so I'm going to relabel this. So instead of having the interval from x sub 1 to x sub 2, I'm going to relabel this as the interval from x to x plus h. So the first x value is x. The second x value is x plus h.
It's
Oh
all.
my gosh, this eraser thing is.
Wait, can you see what's the other
It's all
side?
coming.
Oh my god,
It's
it's
everything is. Okay, alright.
So then when we think about going to label these points, this point would be x comma f of x. And this point here would be x plus h comma f of x plus h. Are we okay with the labeling of this picture?
Yes.
Oh, that was a shit.
So I'm going to go back up here and I'm going to copy and paste our formula for slope of a secant line. And I'm going to rewrite using the notation now that we have in our picture. So the slope of this secant line would be change in y would be f of x plus h minus f of x over the change in x, which would be x plus h minus x, right? What would that always end up simplifying to?
F of x plus h minus f of x all curved. Like we've seen.
This feels familiar.
Almost like a
Yeah. It is, so it's just slope formula, right? Like we have just used slope formula. But we refer to this form of the slope formula when it's talking about slope of a secant line, right? Slope of a function over an interval, rate of change of a function over an interval. This is called the difference quotient. What? Okay, so going back up here. So another representation of slope formula for a slope of a secant line is something we call the difference quotient. Every function has a difference quotient that can be simplified and treated as the formula for calculating the average rate of change of the function over any interval in its domain. So thinking about replacing x with either replace the change in x. Sorry, I thought I was saying to replace x. Replacing the change in x with either delta x or h. I prefer h, just because I think the delta x's can get a little crowded when you're doing a bunch of work. Your textbook, though, I think uses delta x's sometimes. So delta x or h just represent the change in x. Because if we go back to this picture, what does h represent?
The amount by which it differs.
Oh.
Do you see this? Doesn't h represent the length of the interval? X to x plus h. So h is just the length of the interval over which you're calculating average rate of change. So we are going to determine this function's difference quotient. So difference quotient, unfortunately, doesn't have like cool notation for it. You can call it DQ if you want. So thinking f of x plus h, that's going to be the square root of x plus h plus 2 minus f of x is just minus that function all over h. Now there's nothing wrong with this. Technically this is the difference quotient and you could use this formula, like if you know x, like the first value of the interval, like the first endpoint of the interval that you're calculating average rate of change over, and you know the length of the interval, which is h, you can plug those values in and calculate the average rate of change of the function over the interval, which is the slope of the secant line. However, looking ahead where we're going in a couple minutes, it's often useful to think about simplifying so we get this h to cancel. So simplifying with the goal of canceling h. Try to cancel. So thinking about some of the algebra skills that we have just previously used in order to get a common factor to cancel, like a common factor that's not so obvious, right? To try and uncover that common factor and try and get it to cancel. What's maybe a strategy we could use here to try and uncover an h in the numerator and get it to cancel?
Right, there's like square root of x plus h plus 2 over x plus 2.
Say that one more time.
Square root of x plus h plus 2 over x plus 2.
We're heading in the right direction. We're just missing part of it.
Possibly rationalize the numerator.
By
Multiplying by the conjugate, or
by the conjugate over itself, because you're allowed to multiply by one. No one today, when I've asked this question, no one today has said what I call it. What do I call it whenever you do that? Retcon. We're going to retcon. We're going to rationalize by multiplying by the conjugate. A version of 1, which is the conjugate of the numerator in this case over itself. So the square root of x plus h plus 2 plus the square root of x plus 2 over itself. Everyone's like trying to be very like technical in their terminology. Retcon on that puppy. X plus 2. Okay. So remember our goal is to uncover an h in the numerator. If we multiply that out, we can think about difference of two squares. So x plus h plus 2 minus the quantity x plus 2. I'm leaving the h factored out because I want that h to cancel. This should feel very familiar. And then when we think about distributing the negative, you're like, hey, the x's cancel. Hey, the 2's cancel. Which would leave us with h over h times the quantity. That's the square root of x plus h plus 2 plus the square root of x plus 2. And then those h's can cancel. Boop, boop. And leaves us with, I've run out of vertical space, so I'm going to come up here. Leaves us with 1 over the square root of x plus h plus 2 plus the square root of x plus 2. That's okay. This is our simplified difference quotient for f of x. Yeah, but we got the h that I wanted to canceled. It doesn't actually matter.
We just don't like
For average rate of change, it doesn't actually matter. I'm just kind of giving us a little bit extra practice leading into what we're about to do. So this is the simplified form of the difference quotient for this function that can be used as a formula for this function to calculate average rate of change over any interval in its domain. Like conceptually, like being able to find the difference quotient is great. Understanding what it is and like talking about that and understanding, hey, this is something we can use for this particular function to calculate average rate of change over an interval. So the number that would be an output, if you plug in a value for x and h, would tell us how y, on average, how the function values, how the y values are changing with respect to how x is changing. So whether the function values are increasing or decreasing, if they're increasing by a lot or not a lot. So let's use our simplified difference quotient to calculate the average rate of change of f over the interval from 2 to 8. I was getting ahead of myself. Yeah. So notice that our formula for simplified difference quotient has an x and an h. What would we be using? That's not what I want. What would we be using for x here? 2, right? This is the interval from x to x plus h, which means that h is what? How'd you get 6? 8 minus 2. You want the length of the interval. 8 minus 2 would give us 6. So now we can think about calculating the average rate of change, or as Jay said the other day, the AROC.
Is Jay there right now?
Are you there, Jay?
Hi, Jay. Miss you.
I use this video for other years.
Oh, and other people.
Okay, which corresponds to the slope of this secant line that passes through the endpoints at x equals to 2 and x equals to 8.
We just go over.
Okay, so is the difference quotient?
So plugging into our difference quotient, our simplified difference quotient up here. So 1 over the square root of 2 plus 6 plus 2 plus the square root of 2 plus 2, making sure, pet peeve of mine, your division bar is long enough.
Wait, so is the difference quotient the same thing as average rate of change?
It's difference quotient is the formula that is used to calculate average rate of change. It's slope formula, just in fancy notation.
It's like camouflage.
Sort of. Yeah, it's like the camouflage slope formula. So then this ends up being 1 over root 10 plus 2.
And that's it, we're done.
Right, so let's interpret again what this means. Skibbity-doo-dah. This is the rate at which f of x is changing. Well, no. With respect to x. We don't have a unit on x, so just with respect to x.
We could think of it as like per x.
Exactly, if we determined what the decimal version of this was, we would say that the function values are increasing because it's positive, right? So increasing by whatever that value is per x value, like per 1 unit of x.
So like say
Changing-
the COVID case example would be like it's increasing by that number per day. essentially.
Exactly, which we said, didn't we get 500 per day over the interval that we calculated? Exactly. So let me relate back to the COVID-19 cases in just a second. So this is the rate at which f of x is changing with respect to x on the interval, because it's on this specific interval from 2 to 8. Because there's going to be a different, it's not per day here.
Sorry.
So it's going to be, so we're talking about the average rate of change of a function over an interval. So if you use a different interval, you're potentially going to end up calculating a different rate of change because you'll have different function values at the endpoints.
So like if, just for the COVID example.
So let's go back to the COVID example. Let's talk about that one now. So like, let's say that this blue curve was an exponential function that can kind of like model this data. So we chose 2 points to calculate the average rate of change for the slope of the secant line. It was over the interval from March 1st to March 11th. Well, let's say that we wanted to calculate average rate of change from March 11th to like whatever date this is. Won't that be a larger value for rate because it's a steeper slope there for that secant line? Since the graph is kind of increasing, it looks like it's increasing faster. Exponentially, exactly. So it's not so steep and then it changes to being steeper. So the same thing with any function, like unless you're dealing with like a line, like if you have any other sort of curve, depending on what interval it is that you're calculating average rate of change over, you'll probably get different values. Right, Mealy?
Yeah. Sorry, I didn't finish it.
Okay.
I just have to fill it.
Oh, I had the little picture down here. So, again, we calculated, let me label this picture. We calculated average rate of change over this interval. Spam. We calculated average rate of change over this interval, which was March 1st.
This works.
Which is March 1st to March 11th, okay? And the question that I have over here is what if we wanted to know the rate at which new COVID-19 cases was increasing on March 5th, 2020? How could we calculate that rate with what we know? So like what we currently have in our toolbox, does anyone have an idea for how we could try and calculate the rate of change on March 5th, so on a particular day? Or maybe get a closer approximation to the rate of change on that particular day, March 5th.
Like, just look at that day and then the day before.
What would you be doing if you did that?
Instantaneous rate of change.
Well, you're trying
Wait,
to,
sorry,
you would be
can you
using secant line,
Can you repeat it?
right? So Drew's idea was to look at March 4th, which I believe that's x equals to 4, right? This would be March 4th?
No, it's March 5th, because that's 4 days after March 1st. We calculated March 1st to March 10th.
Sorry, March 5th. So, but we want to calculate, so didn't you say calculate the average rate of change from March 4th to March 5th? So would that be this day to this day? Like calculate the slope of that secant line? What are you doing? That would be a better approximation, right, of the average, or of the rate of change on March 5th than using this interval.
Yeah.
What have we done? What's different in using those two values, Alan?
You've like gone closer to the limit of it. Like you've gone closer to the value.
What did we change?
The X.
The H. What did we do to H? We shrunk the H. We thought about making the H, the length of the interval,
1.
smaller. Right, smaller than what we had previously.
You can't get 0.
Can you? Can you?
It's in the denominator.
Oh, I don't know. Like, can you?
Oh.
So, what we're saying is if we wanted to determine the rate at which new COVID-19 cases were increasing on March 5th, 2020, the one idea that Drew just came up with was trying to come up with an interval that's close to March 5th and is a small interval, right? So he said calculate the average rate of change from March 4th to March 5th. Okay, that would be a pretty good approximation. What if you calculated the average rate of change from like, let's say like x equals, so March 5th corresponds to x equal to 4, right?
Yeah.
So what if you calculated the average rate of change from like 3.999
The
to
limit as
4?
x approaches 3 or 4 or whatever of f of that.
Well, h is the size of the interval that you're calculating average rate of change over, right?
The limit is x approaches h.
So we're thinking about making h smaller and smaller and smaller.
Horizontal velocity.
You're throwing things out now, right? So we are thinking about making the size of the intervals, which is h, smaller and smaller. In other words, thinking about h approaching 0?
Why can't you just make it 0?
I don't know. Why can't you just make it 0? You just told me a minute ago why you can't make it 0.
Because h is on and on.
Line would be 0.
Then your change in x would be 0, and you're like, well, that's not allowed. Hopefully I think you were all thinking limits. You okay over there, Arjun? You're, yeah, okay. Limits! Limits! Woo! We know limits! You guys,
Clearly not.
to calculate the rate of change at a particular moment, like on a particular day, means we're trying to calculate the instantaneous rate of change of the function, or the rate of change of a function at a particular point, which means we're calculating the slope of the tangent line to the curve, right? We calculated slope of secant line to find average rate of change over an interval, but to calculate instantaneous rate of change, we are finding the slope of the tangent line. And to do this, we're thinking about making the size of the interval that we're calculating average rate of change for smaller and smaller and smaller, so h approaching 0. Are we following this? This is like not a great moment for Alan to have stepped out. This is like, oh.
He's bleeding.
Why is this?
Oh, his nose is bleeding?
No, he was like, I don't know, he's bleeding.
Oh my god.
So the slope of the tangent line at tangent line, do we all know what a tangent line is from like geometry?
No.
No.
I know
That
the
was so
SAT.
long ago.
The ones on the SAT, the tangent lines are literally the hardest questions ever.
You had tangent lines on the SAT, maybe that's why it doesn't go on.
Okay.
Well, not on this last one. But like,
So you guys, March 5th, if we wanted the rate of change on March 5th, we're wanting to calculate the slope of the line that touches the curve at March 5th and nowhere else. At least, oh my God, this is driving me nuts.
Turn it off.
But it's going to take time to do that.
30 seconds.
I think we can take our Bible version.
Once you get
No.
used to it, it just clicks.
I still don't understand it. Okay, so we are essentially trying to calculate the slope of this line that touches this curve at this point and only this point in the neighborhood of this point.
But like, couldn't you draw?
So the curve could extend, and like if you imagine the tangent line extending, it could intersect like far away, but like if you zoom in just near this point, the tangent line touches the curve only at that one point on the function in that neighborhood.
What is the tangent line again? Just
That's what I'm saying.
Graph 1? once?
No, it touches the graph at exactly one point in that neighborhood. So like if we're talking about the tangent line, so in green here, the neon green, I attempted to draw my tangent line. It touches the curve at that point, and only that point in this area.
But if it only touches at a point once, can't the slope kind of be anything? Because, like, say you
Well,
have-
no. So, hold on. So if we're thinking about taking the limit as h approaches 0 of our difference quotient, okay, that means we're thinking about making these intervals smaller and smaller and smaller for calculating average rate of change, right, until it becomes just the slope of the tangent line.
There's one reason here that's just like, do you see? Yeah.
Okay, you guys, hey.
Sorry.
This limit results in a formula for the function that will allow you to calculate the instantaneous rate of change, also known as just the rate of change, to all points on the graph of the function that have a tangent line. So for all x for which the limit exists. We call this formula, dun, da, 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 the derivative of the function. Okay, the derivative, oops,
I thought this was like so complicated, it's gonna come up like in unit like 17.
no way.
You just
Oh,
missed
already learned about
derivatives.
derivatives?
Bunch of stuff.
So again, I'm gonna talk through this. So the derivative of a function is a formula that you can come up with for that function that can then be used to calculate the instantaneous rate of change at a point on the function. Like, so how the function values are changing with respect to x at that particular point. Yeah.
I do realize this is not a good time, but I think I just start like doing it. Can I go?
Yeah.
Wait, I have derivative like d of something, I mean d.
Okay, well, we're getting there.
DMX.
We are developing your conceptual understanding of what a derivative is right now. So, provided the limit exists for all x for which the limit exists, f prime is a function of x. So, a derivative is its own function. In physics, you've seen that, right? Like, you guys have looked at the connections between the graphs of a derivative and its original function. Like, the derivative is a function, and it has the relationship to the original function that it's this formula that you can use to calculate the slope of the tangent line or the instantaneous rate of change. The process of finding the derivative of a function is called differentiation. Okay, go through some vocabulary so we can communicate and understand directions. A function is differentiable at x when its derivative exists at x, and is differentiable on an open interval from a to b when it is differentiable at every point in the interval. That should feel kind of deja vu to, or similar to our discussions about continuity, and we're going to get into the connections between continuity and differentiability.
Wait, so the limit is finding,
So when we take the limit as h approaches 0, so think about making the interval smaller and smaller and smaller of the difference quotient, that gives us this formula that you can use to calculate the slope of a tangent line.
Right.
And the tangent line touches a curve at exactly one point, and the slope of the tangent line corresponds to the rate of change of the function at that particular point.
So the function at that particular point
So-
is derivative? Or the derivative is
No,
what
the
you find?
slope, the rate of change of the function at that point is whatever the derivative is evaluated at that x
So
value.
what's the derivative, like, what's an example of a derivative? Is it like a function or like
A derivative
It's
is
like a
a
line
function.
a line?
No. The number, the interpretation of the number that is an output of the derivative is the slope of a tangent line to a point on the graph of the original function. Can you say that one more
Slope,
time?
it's a slope.
Yes,
It's
it's
a
a
slope.
slope, it's a slope.
Okay.
So to go back to here, Like let's say that this is an exponential function. This blue curve is an exponential function. You don't know yet how to find it, and we're not going to learn today. But if we knew what the rule was for the derivative of this function, if we wanted to calculate, you could even refer to it as the slope of the curve, like the slope of this exponential function. Like we've talked about slopes of lines, but if you wanted to find the slope of the curve or the rate of change of the curve at a particular point, you could take the x value and plug it into the derivative, and it would give you the slope of the curve at that point.
At any point?
Wouldn't it approach infinity?
In the domain, as long as there is a tangent line to that point.
Wouldn't it approach infinity then? Because h is on the bottom of.
Well, hold that thought. Good question. So before we get into that, I do want to show you guys some other notations. So the notation up here that uses function notation, this little like caret, that's read as f prime of x. That's like if function notation is being used. It communicates what the connection is between the derivative and the original function. So these are all notations that you may see come up in your textbook, other textbooks, future calculus courses, maybe in college, maybe in physics, maybe in on the AP exam. Like these are different notations that you need to be familiar with. So there's f prime of x, y prime, like if your function is of the form y equals, like y prime would be appropriate. The most useful one, I think, to understand is dy over dx, which is read as either dy dx, or you'll often hear me say dy over dx. Or the most useful reading of it would be the derivative of y with respect to x.
So that's just the slope, right?
Exactly, but it's the slope of the tangent line, like the slope
Yeah.
at a particular point, right? Because you're thinking d for delta, I'm assuming?
No,
Like
it's-
delta y over delta x?
No, I was saying the derivative of y with respect to x would just be the derivative y, what lies.
So,
Right?
one interpretation of slope over an interval, right, would be change in y over change in x, which you guys have seen before as being delta y over delta x. When delta x gets so infinitely small, that's when we end up using dy over dx. Okay, because we're talking about the rate of change at a particular point and not on an interval. The other notation you might see, like d over dx of, like with y in the brackets here or in the parentheses, or you could see like d over dx of f of x. And this is just, it's like an operator. It's indicating that you're taking the derivative of whatever inside here
Oh, so like,
with respect to x.
oh,
And for now, we are just thinking about differentiating with respect to whatever the independent variable is. We will eventually be thinking about differentiating with respect to a variable that's not the independent variable, like a third variable. But we're not there yet. So for now, we're usually talking about calculating the change in the function value with respect to the change in the independent variable.
Wait, what was that?
What time are we out of here? Is it 37?
Yeah, that's pretty easy.
Wait, what did you over dx again?
I think it's 30.
d over dx, it just indicates that we're taking whatever's inside the bracket, you're taking the derivative with respect to x.
Are we okay? So let's go ahead and find the derivative. Let's use the limit definition. This is a moment, you guys. You're about to find your first derivative. So we're going to find the derivative
This is exciting, actually.
of y equals x squared plus 3x. I'm going to use dy over dx as my notation. But using like y prime would have been appropriate as well. So we are thinking about taking the limit as h approaches 0 of f of x plus h. So thinking about replacing all of the x's with x plus h.
We just go straight to using.
Nope.
This. Oh. Yeah. Oh, I know.
I thought you were going to ask something else. For those of you that know the shortcuts, you're not allowed to use them yet. You can use them as a mental check, but you may not use the shortcuts. You have to earn the right in this class to use the shortcuts, and we're not there. And I think that using the limit definition of the derivative conceptually, or helps you to conceptually understand like what a derivative is, right? It's thinking about taking the limit of the difference quotient of the formula to calculate average rate of change and making those intervals smaller and smaller and smaller. Okay. So you guys, what happens? This is a limit. What happens if we use direct substitution?
Undefined.
Indeterminate form. Indeterminate form, 0 over 0. Like if we go up here, you guys, do you notice that that will always happen with direct substitution? If you set up your difference quotient, which is why, because we know when we use direct substitution for h, that's what's causing 0 over 0. So we know that our work is to uncover an h in the numerator that will cancel with the h in the denominator. This is why we've been studying limits, you guys, to get us to this point. What can we do here? What method should we use?
Sledgehammer.
Sledgehammer! Okay, so let's brute force, multiply everything out. Sledgehammer that one. Okay, and don't do any illegal algebra while you're doing it.
I love equalizing algebra.
Okay, and then best part of sledgehammer, what cancels? Cancel, 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 cancel. And then we're like, hey, there's a common factor of h left in the numerator that did you guys notice that I have given you limits like this? You didn't know what they were, but I have given you limits that looked kind of like this. Okay, once we've gotten that h to cancel, I'm going to write out the extra step, although you don't have to. From here, after we have gotten those h's to cancel, then you can use direct substitution, and you're like, hey, 2x plus 0 plus 3. 2x plus 3 is the derivative of this function. This is the formula that you can use to calculate the slope or the rate of change of this function at any point that's in its domain.
So then,
Oh,
why is there 3? Because
I don't know. Why is there?
at any point in the domain.
Okay. The derivative is its own function. Okay.
You use it to calculate the slope of the
We use it
line.
exactly.
This
It calculates slope. It calculates. Its
It's not.
outputs are slope.
Okay,
So don't be looking at it trying to
It's all
like
line.
see slope. No.
Oh,
Its
Oh.
outputs, its function values
will correspond to the slope of this function
So that's the slope.
at different points. Yes, it is.
Is this formula the derivative?
This is the derivative. 2x plus 3 is the derivative of y equals 2x squared plus 3x. Let's do another one.
Wait, what's the formula for the notation? It's like d y over dx.
I used dy over dx. You could have used y prime for this one because it was y equals. My next one says find dy over dx. So use the notation that's in the problem. Dy over dx will be the limit as h approaches 0 of 1 over x plus h,
What age?
difference quotient, minus f of x all over h. If you try direct substitution, you get 0 over 0. So then you're like, what do I have in my toolbox here? Deal with complex fractions.
Whoa.
No,
The one where you multiply by.
Yeah, LMC.
Oh, these complements of.
LCM.
Yeah, there's different. That one's like kind of tricky because it's really the least common denominators of the complex fractions, right? So like what version of 1 would we want to multiply by here, you guys?
X times X plus
Perfect. X times X plus H over X times X plus H. Okay, so thinking about distributing in the numerator, so we'll have the limit still as h approaches 0. The x plus h's will cancel, so we'll have x minus, the x's will cancel, the quantity x plus h over h times x plus h. We're almost there. Distribute the negative. So we'll have the limit as h approaches 0 of negative h. I'm going to write out this extra step. Negative h over h times x plus h. Where we see the h's cancel, so we're left with a negative 1 in the numerator. Don't throw the negative away. Common mistake.
Wow.
And then use direct substitution, and we end up with negative 1 over x squared.
0 focus.
You doing okay? All of my classes today, you guys, have been just kind of slogging.
We were like 24 ones.
Yeah, I'm talking before this.
We're after lunch.
Maybe I have no excuse.
This morning we were blobbing.
Lunch. We're after lunch. It's always like most times.
Oh, so we're
Wait,
just,
no,
this
last-
class is always just going to be
Last period is
Lob.
so sorry.
blah, blah.
No, because you just ate lunch, and you were just used to like being outside, and now you have to go inside. It's like.
Weren't you inside,
difference
inside?
from outside to inside.
Weren't you
Difference.
inside at the
The
student
H's.
council
Yeah.
meeting? Weren't you inside at the student
yeah,
council
Yeah,
meeting?
That's why I'm the most energized. Actually, not everyone else here was also.
I think Alice was the
Okay.
I think Drew is the most energized.
Drew is always the most energized.
Drew is still energized right now.
100%.
Not right now. Does everyone, like, why don't you, like, stand up, do, like, 5 jumping jacks or something?
Get up. Get up right now.
Processing. Okay. So here's what I want to do. Let's do, who's a dog? Oh, great. You two are going to work together. Okay, who's a cat? A hamster.
I got a
A
brother.
fish.
Because my dog.
A little brother.
Ew,
All
I
right.
don't want to work with a
You
grown
two
guy.
and then you two. So go ahead and find f prime for the square
Take it easy.
Yeah.
Wait, we already done
Yeah. Wait.
something like this.
Wait. Can you scroll out to A? Oh wait, it's frozen. Is this supposed to be? Oh. Is this supposed to be H?
Are you seeing the Mickey Mouse?
Yes.
Clubhouse?
Is that supposed to be H?
Yeah.
Oh, that makes so much more sense.
It says it because H represents the length of the interval, right? So we're thinking about making the interval smaller and smaller and smaller.
Okay.
So H approaching 0.
Okay, fine, Drew.
You have to use the conjugate.
Ow.
Multiply it
You have
up.
to retcon.
One over.
Usually you have for the first.
I'm confused. Oh wait.
You're confusing me.
Do we have to do? Oh, we have to do A, B, C, D.
You can look to the next ones if you want with your partner if you finish finding the derivative.
I don't think
My
I
article for newspaper is getting censored.
Wait, is it actually?
They're saying they need a counterbalance. If I remember right.
That's why they were like,
that's
this
what I asked for
one's.
the Trump.
Yeah.
Hey.
Wait, what's your article? Oh wait.
It's my endorsement of the candidates. They don't want that because they don't like.
Are you doing editorials?
Yeah.
I'm not writing an article right now.
Boo.
Hey. Shh. You're talking about finding the derivative. Or what is the slope of f at x equals to 1?
Slope is 1.
It's 1 over 2 root x.
Oh,
I'm not done.
The difference
Very
question is minus
possible.
the next thing, right?
Is it?
We do all of it, Mr. Shep?
Yeah, you guys can start talking about the next parts if you find your derivative.
That's the
I
slope.
think it's 1.5. Yeah. It's just like an x.
What is that?
Can you?
Are you already on C?
Yes.
So,
Wait, like collaborating. You guys, this is like your biggest areas of growth. Like you guys need to work on collaborating better. Like not just sitting near each other and be like, hey, what'd you get? Being like, okay, we need to find the slope of the graph of f at x equals to 1. How are we going to do that?
Wait,
How are we gonna
Wait,
do
What
that?
is the slope of the graph?
you just
Wait,
bring
so
it
what
up.
do you get for it?
So,
I don't know if I got
actually
it.
it's
I got it.
You finished it?
So all you do
Wait, I didn't do A. Oh.
That's just
That's
plug it in.
what I'm getting from
Find the
there.
equation,
I got
so I get
Wait.
slope.
What's
X.
2? No, it's 0. Wait, why is it minus
Plug it back
x?
into the
Is it
original
plus?
line. Like,
Why is it minus?
But f prime of x is
No,
the
it's
slope
plus.
equation.
If H is
F
0.
prime of
So
x
this
is
is
equal.
plus.
If it's
Oh,
minus
it's
x,
Oh, it's root of x or minus.
I got root of x plus.
Yeah, the derivative.
Thanks, Drew.
It's the same thing as d over y and
Oh,
y over d.
Yeah, the derivative
I
is
mixed
the
up
same
my
value. Harry, did you get a half for b?
Yeah.
Did we, you guys, did we all get f prime?
Oh no.
What do we get for f prime?
1 over 2 root
1 over
x.
2 root x.
Okay, so when the question asks, what is the slope of the graph at x equals to 1? That's the same thing as asking for what is the slope of the tangent line at x equals to 1, because the slope of the tangent line will represent the slope of the graph at x equals to 1. So if you're trying to find m tan, that's going to be f prime of 1, which is 1 over 2 root 1, or 1/2. And then what is the equation of the tangent line to the graph of f at x equals to 1? Do you guys remember my favorite form of the equation of a line? The superior form of the equation of a line? Point slope form? Because, hey, we know an x value. How could we find the y value that goes with that x value?
Oh, we do like y minus y1.
Right, but we need the y that goes with that x. How do we find that y?
Guess and check.
Plug it into the actual equation.
Plug it into the original equation, you guys. So you're finding f of 1, which would be 1 comma 1 in this case, right? Because the square root of 1 is 1. We have the slope, so the equation of the tangent line at 1, 1
will be y minus 1 equals to the slope times x minus 1. This morning they were all trying to find the equation in slope-intercept form. I was like, you guys, you don't need to do that. Especially if it's a free response. Point-slope form is the equation of a line. You're done. And it is very likely that some part of a free response question could end up asking you for the equation of the tangent line and then to use it somehow. And then it's also nice because, like, if you were using it to approximate a function value, then you're like, oh, hey, let's just add 1 to each side of this equation.
When you get the 1 comma f of 1, is that supposed to be 1 comma f prime of 1?
No, I want x comma y. So x comma y would be the point that's on the function f of x, like on the square root of x.
So you use the original function, x squared root.
Correct. When you want to find the y value that goes with the x value, use the original function. All right, you guys, your homework is